We've gotten referencing out of the way, so now we can actually start moving the drive in earnest. We're going to look at positioning, moving to specific locations. Two important points I want to talk about before we go any further. The MoviDrive B's native positioning unit is the increment. That may seem a little odd to you since when we position, we tend to think about real-world units like inches or millimeters. The increment is a unit that comes from encoders. But that's what the MoviDrive B is working with. It's basically counting increments coming back from one or more encoders and deciding how far it's moved. So it's not entirely surprising that it uses the increment. There are certainly ways that we can translate from increments to real units. We'll be doing that before this session is over. But do be aware, at heart, that's what the MoviDrive B cares about. Second point, I've said this several times, but I'm going to say it once more just for emphasis. All motor encoders, the ones connected to the X15 connector on the encoder card, automatically get scaled to 4096 increments per revolution, regardless of their true resolution. So if they've got a lower resolution, it's scaled up. If they have a higher resolution, it's scaled down. It's always 4096 increments per turn of the motor shaft. Now let's look at a typical positioning scenario. This is similar to what we used for our referencing discussion. We have a horizontal track with a moving carriage that moves left or right across it. There are limit switches at the ends to keep it from going off the ends of the track. And we have a travel distance, which in this case is 10,000 increments. Now I see a hand in the back of the room. Somebody is saying that is a ridiculously small number of increments. That would take about 2.5 turns of the motor to go the entire track distance. You're totally right. I admit to that. Why am I using such a small number? Simply because I don't want to have to quote really long numbers over and over and over. So I've kind of scaled this application down to something really small just to keep it manageable. Doesn't affect the examples, everything's still perfectly true and applicable, but do be aware that in real applications, in most cases, we're dealing with far bigger numbers of increments than we are here. All right, that said, let's move on to the first type of positioning. It is the simplest, and it is called relative positioning. You're moving a positive or negative offset from wherever you currently are. You don't need to know your true position along the track. All you're saying is, I want to move positive or negative from where I'm sitting by this distance. Generally, we treat positive as clockwise and negative as counterclockwise. Of course, it's possible if you have a gearbox that changes the shaft rotation direction, could wind up going the other way. But for our examples here, we'll just assume that positive means clockwise to the right and negative means counterclockwise to the left. That is relative positioning. Let's look at some examples. Let's say that we want to move 2,000 increments counterclockwise or to the left from where we're currently sitting. What do? Very simple, we issue a go -2000 positioning command. And that says take where you currently are and go counterclockwise 2,000 increments. And as soon as you do that, boom, you will move to that location and stop. Pretty simple. Now, if I say move 6,000 increments in the positive direction, it's going to do this. It's going to take wherever I happen to be, and it's going to move clockwise, counting increments from the encoder until 6,000 has gone by. So if I say go positive 6,000, that's what's going to happen. Again, no big surprise. Relative positioning is very simple and easy to understand. Now, there is a second kind of positioning available to us called absolute positioning. It is a little different. You're moving positive or negative. Again, it's an offset, but it's not from where you are. It's from the machine zero position, the MZP. Everything is essentially absolute based on that position. Now, of course, what that means is the VFD must know where machine zero is. And in this case, the sign doesn't tell the direction to move. The VFD figures that out. It tells you where you want to be in an absolute sense along that travel distance, and the VFD is going to figure out the direction to move the motor. So in this application, we have a longer travel distance. It's 150,000 increments. Let's establish a few other things, and then we'll do some positioning. Let's say the MZP is right here. It's not in the exact center, but it's sort of near the center. That is 0, and everything else is effectively referenced to that point. For example, 0 is the MZP. Maybe we have a distance of plus 25,000 increments in front of it. We're currently sitting at minus 25,000 increments behind 0. And there's a further distance of minus 50,000, which is more to the left of that position. These are absolute locations. They're not just simple offsets. They're offsets referenced to 0. That is the big difference. So if we're going to do a positioning operation, if I say go to minus 50,000, that doesn't mean move 50,000 increments to the left. What it means is locate 50,000 increments behind MZP and go whatever direction it takes to get there. Now I'm sitting at minus 25,000 increments, and minus 50,000 is another 25,000 to my left. So when I execute that go command, that's what's going to happen. I'm going to move to this location. The VFD figures out where MZP is, it figures out where I am, does the math, and it concludes what direction to move and how much to move, and then it does it. Similarly, if I said go plus 25,000, it doesn't move to minus 25,000. It's going to figure out where 25,000 is relative to the MZP. And it does that and winds up way over here. I hope you can see the difference between absolute and relative positioning. There are a lot of similarities between them certainly, but there are also some key differences. Now, what if I want to move in real units? I don't want to work with increments. Can I do that? Well, the answer, of course, is yes, you certainly can, but you're going to have to do some math to relate real units to increments, because that's what you need to give the Movi drive when you tell it position itself. So let's take our identical scenario here and now try to associate this with some real units. Let's say our travel distance is 25 meters, which is 25,000 millimeters. All right, this is a realistically sized travel distance, so we're no longer fudging with little tiny units here. We are going to be working with full-size units. This is a fairly long travel distance, like maybe something you'd have in an auto plant, and we're going to set it up so we can position to the nearest millimeter, somewhere along this distance. How do we set this thing up? Well, if you think back to our math session, which was a very long time ago, you remember that we wrote a program that related real units to increments for a roller-type conveyor belt. Well, this is basically the same kind of scenario. In fact, we're going to reuse some of that code for one of our example programs before we're done with this session. Now, when we're dealing with a situation like this, we need to know the application parameters. We need to know things like roller diameters, and we need to know gearbox ratios and various other things. Let's step through the math here and kind of work this out. We're going to say that the carriage moves by rotating its wheels. All right, so this isn't like a roller conveyor exactly, but actually, if you stop and think about it, it really is. But instead of moving a belt, the wheels are just moving the carriage. We need to know the wheel diameter so we can figure out what linear distance one rotation of the wheel is going to produce. Well, in this case, I've said our wheels are 150 millimeters in diameter. That means to know the linear distance one turn of the wheel makes, we need to know the wheel circumference. And of course, we calculate that with our old friend, pi times d. We multiply 150 millimeters times 3.14, and that gives us a circumference of 471 millimeters. If we turn that wheel one rotation, we're going to move 471 millimeters across the track. However, what if there's a gearbox in the picture? As we know, gearboxes slow the motor down, therefore they increase the number of turns you need to rotate to go the same distance. Well, we'll say that we've got a gear ratio of 7.12. So you very roughly have to turn that shaft about 7 times as much as you think you do to move 471 millimeters. All right, we're going to calculate the exact amount because, of course, we really do want this to be accurate. What we do is we take the circumference and we divide it by 7.12, and that tells us that one motor revolution doesn't move us 471 millimeters, it moves us 66 because the gear ratio slows everything down. One rotation of the motor is going to give us 66 millimeters of linear travel. Okay, so far so good. Now we need to relate that to increments, and so we need to remind ourselves when the motor shaft turns, it's going to turn the encoder, and it's going to turn it directly, not through the gearbox. We need to relate motor encoder increments to linear distance. Now we know, of course, that if we're using the motor encoder, we get 4,096 increments per revolution. To figure out the relationship of increments to millimeters, we just take 4,096 and divide it by 66 millimeters, and that gives us our scale factor. It says that for every 62 increments we count from the encoder, we have moved 1 millimeter. All right, so if we want to move a specific distance, say we want to move 25,000 millimeters, which is that 25-meter distance. How many increments is it going to take? Well, we take 25,000 and multiply it by 62 increments per millimeter, and that tells us we have to move a whopping 1.55 million increments. That's how many increments we have to count to traverse the entire track. Okay. I know that was a lot of math, but I hope you understood it. If you don't, maybe you need to play this section over again because you will eventually be writing a program that implements this concept. Be sure you understand it. Using this math, we can take the actual unit distance we want to travel, we multiply it by our scale factor. That gives us increments, and that's what we feed to our IPOS program. That's what the MoviDrive B actually moves and counts. It's not actually as painful as it feels at first. It's pretty straightforward. And once you've written a program, I think you'll be pretty comfortable with. Okay, moving on to something else. We need to talk about the positioning, speed, and acceleration. And that means we have to visit the parameter tree. These are some of the parameters that have an influence on positioning. First of all, there are two travel speeds in parameters 913 and 914. This is the speed that when you give the MoviDrive B a positioning IPOS command, it will move. And they can be different, of course. Right here, they're both set to the same value, 1500. As you recall, since I had a servo motor, I set mine to about 4,000 RPM. That was about 10% less than the motor's maximum speed. Of course, you can certainly pick slower speeds if you want. You don't have to pick maximum. That was more an upper limit, but right now it doesn't really matter. Simply be aware these are the two parameters that you have to adjust to pick the positioning speed that you wish to use. There are also two positioning ramps. They set acceleration and deceleration time, and like all MoviDrive B ramps, they are specified in time units of seconds, which may feel a little weird, but that's just the way the MoviDrive B works. Right now, they're set to a second each. That's fine, but of course, you would tune that to whatever your application needs. And then there's also a ramp function parameter that sets the shape. Right now, I've just got a linear shape selected, which is perfectly fine for what we're doing. But there are certainly other kinds of ramps available. Do be aware, however, some of the shapes do not use an acceleration and deceleration time that's separate, which means they will only draw from 911. So to understand that better, you are going to have to dig into the MoviDrive B manual and read about these parameters a little more. We're not going to go into it any further. Do be aware the program can override these, and in fact, in a later session, not too far in the future, you will learn to set all of these from within your IPOS program, so you don't even have to set them from the parameter tree. Okay, let's get to the IPOS functions that perform positioning. There are just two. The first is called GoRel. And I think you can guess what it does. It does relative positioning, so it's going to move relative to the current location. Now you notice it has two parameters available called type and pos. Type indicates how you want the function to behave, and there are only two types available. And this should be familiar. They're called wait and no wait. So this function can be either a wait function or a no wait function. That's all you can do with type. Tell it how you want it to behave. Do you want it to start positioning and wait until it's finished? That's what you do with go wait. And if you want it just to move on, then pick no wait. Of course, do be aware if you use the no wait version of this, you're going to have to figure out when it arrives at the destination. And you can guess you're probably going to look in status word and check a bit. Pos is either a constant or a variable, and it contains the distance you want to move in increments. And remember, that should be a signed value, positive or negative, because that indicates the direction of travel. Okay, well, it's time to write a program. So we're going to create a new program, program 9. However, we're going to reuse some of our code from program 8. So you probably want to make a copy of that program and use it so you can save yourself some coding time. Here's the application we're going to implement. We are going to do a positioning application for a canning and palletizing machine. So it's something like this. We have a long linear track. At the left end, we have our start position. You can see the little carriage that's going to move the cans, and we consider that our 0 position. So that's start. All right, next along the track, we have a can filling machine, and it's located at 30,000 increments clockwise of the start position. There's a weigh station at 65,000 increments relative to the start position. And it's going to weigh the can to make sure it's got the right amount of material in it. And then finally, we have our palletizing machine at the very end at 110,000 increments relative to the start position. This is going to pick up the can and put it on a pallet. Here's what the application needs to do. It's going to wait and watch digital input 12, and it's going to wait for a pulse to come in on digital input 12. It's going to expect it to be off, and it's going to look for an on-off pulse. The idea is if this were a real application, maybe a PLC or something is going to transmit that pulse to the Movi drive. Now, what does that pulse signify? It means that a can has just been placed on the carriage. That's the signal to begin. So as soon as you see that DI12 pulse on, off, you can assume the can's in place and you can start your motor and move the carriage, and you should move to the fill position for the can to be filled. You can assume the can will be automatically filled as soon as it arrives, but you need to wait for 10 seconds because that's how long it takes to fill. When 10 seconds has elapsed, you may move to the weigh station, and you must wait there for 5 seconds while the can is weighed. Then you may proceed to the palletize station, where you should pause for 7 seconds to have the can removed. And once that time is over and the can presumably is gone, you return to the start and you're going to pulse digital output 11 on, off. And that is a signal to the imaginary PLC that you have returned to the beginning and it can place another can on the carriage. That's kind of the idea. So the PLC communicates with you with DI12. You communicate back with it on DO11. Now, these are your program parameters here. You can see by looking at these that a lot of your existing code is already doing this. Here are the tasks. If DI10 is on and DI11 is off, then perform unconditional referencing that doesn't wait and uses the cam plus the 0 pulse. It flashes DO10 during referencing. You can halt it with either control or inhibit or enable by turning it off. And the light connected to DO10 should stop flashing when referencing completes or is halted. Guess what? That's all your existing code. So that part of your program's already written. You don't have to do anything. You can just use your current code. Here's the new code. if DI10 is off and DI11 is on, so that's the opposite condition here, you need to wait for DI12 to pulse on-off, move to the fill station, that's at 30,000 increments, and wait 10 seconds. Move to the weigh station, which is at 65,000 increments, and wait 5 seconds. Move to the palletized station, which is at 110,000 increments, and wait 7 seconds. Return to the start position, which is at 0 increments. Turn DO11 on, and you can just turn it on for half a second and then turn it off. Use only relative positioning for this program, and I would like you to use constants for all the positions and times so you could change your application easily. So don't code it right into the program. Use constants for all those locations. And here's a little tip. Remember that those increment values I gave you are the actual locations of the stations, but you are doing relative positioning. So that means you've got to think about the relationship of each of those. And here's a second helpful tip. Remember, since you're reusing some of your old code, that we had you wait for all the switches to be off and then for any switch to be on to sort of start things rolling. Well, you can remove that code from this program. You actually don't want it. You'll find out later this program is eventually going to develop into your final sort of senior project code. So you don't want that. So remove those two while statements that did that wait from your existing code. Okay, that's all I'm going to say, other than pause the video and give it a try. All right, well, I hope it went well for you and you successfully created your positioning application. If you had any problems or struggles, of course, when you look at my code, maybe that'll clear them up. So let's take a look at my code and see how I approach this problem. Okay, well, we have our program here, and as I mentioned earlier, since it contains a lot of code from the previous draft, I'm just going to keep that. What I'd like to do is go through the things that are different and put a bit of emphasis on the new code. All right, let's start with our variables and constants. Remember, I said we need to use constants for all the positions and times. So here they are. I've identified each station by name. This makes everything readable. I've also commented things pretty carefully, and I've even provided units, increments, and milliseconds. Always give people as much information as you can in comments. I'd like to call your attention to the positions, though. Notice the fill position is set to 30,000. That is, in fact, the distance from the start position, which is 0, to the first station. But if you look at the second one, that may puzzle you. It's set to 35,000 when the actual position is 65,000. You may wonder why. Well, this goes back to that hint I gave you. Remember, we are doing relative positioning, where you move relative to where you currently are. All the positions I gave you were relative to the home position. When you're at the fill position, to reach the weigh station, you don't move 65,000 units, you just move 35,000 units, and that takes you to what would be an absolute position of 65,000. So I hope you caught that and you moved to the right places. Notice when we go back home, we go back minus 110,000 increments. That's because we're going back to 0. And again, we're using relative positioning, not absolute positioning. Nothing fancy about the times. They're simply the times in milliseconds. Nothing unusual there. All right, our other constants are pretty much identical to the previous program, but there is one new one right here. This is that signal that we flash when we go back to the home position to signal the imaginary PLC that we're ready for another can. I've called it at home, and this is just the bit number of DO11 in opt-out IPOS. Nothing special here. All right, let's move on. All of our code up to this point is identical with the previous program. This handles referencing. There is only one difference. I've taken out those 2 while loops that first of all confirm that no switches are on and then that wait for any switch to turn on. As I said before, we don't need that here. Eventually you'll understand why. At this point though, just suffice it to say I've taken those 2 lines out. All I've done is I've re-enabled my access in case there's an existing access stop, and then I check DI10 and DI11 to see what I should do. Remember, if DI10 is on and DI11 is off, we're to go into referencing mode. If DI11 is on and DI10 is off, we go into positioning mode. And if both of them are on for some reason or any other switch is on, we do nothing. So this code doesn't do anything new, but we do have an else statement after it, and this is where the new code comes in. We now check, is DI10 off and DI11 on? If that's the case, we go into positioning mode, and you can see here now we do have our positioning code. The first thing we do is we wait for DI12 to pulse on and off, so we use 2 while loops, first to see if DI12 is off, and then to see if DI12 is on. Once we get through that, we go into our positioning, and all we do is a bunch of go relatives. We use the wait version of it. There's no reason to use the no wait in this case because we don't have the requirement that we be able to interrupt positioning or anything. So go relative with go wait is fine. We use the constants to move to the locations, and then between each positioning operation, we have calls to the wait function for the required pauses. Once we've gone back to the home position, we need to flash the home bit to signal the PLC we're back in the home position. We just do a bit set and a bit clear operation with a wait 500 in between, and that is it. As you can see, this code is not very complicated. It really is just an extension of the previous program. All right, well, let's compile it and make sure it's okay. And it is, compiles just fine. So we're going to run it. And now we need to exercise all its functionality. I need to make sure my limit switches are both switched on and controller inhibit and enable are switched on. Nothing new there. And then I'm going to go ahead and check each operation. I'm going to do referencing first to make sure it works. Then I'll do positioning, and you can see that that works out. So here we go. Okay, I have my control box here. I'm going to trigger referencing by turning DI10 on. And I'm not going to leave it on, because if I leave it on, it's just going to jump back into referencing again as soon as I finish it. That's because we took those 2 lines of code out that waited for all the switches to be off. You'll see in a second why we did that, but I'm going to trigger referencing by turning DI10 on and off. You can see we're in referencing mode. I'm going to trip the cam. We slow down. I'm going to come off the cam. We stop. We go past the 0 pulse, and now we're referenced. All right, so that works. That piece of code is fine. I'm now going to turn DI11 on, which will start positioning. So I flip it on, and nothing happens. Well, remember, we've got to pulse DI12 to on and then off for it to begin, and then we should see it go to each of the different positions. Let's watch this. I'm going to pulse DI12, and we start positioning. There's the first. We're waiting now while it's filling. Now it moved to the way station, and it's delaying again. Now it moved to the palletize, and it's waiting again, and it should go the opposite direction to return home. And it just did, and it blinked DO11 to indicate that it's back at the home position. Okay, so our code worked. Now, let me demonstrate something. I have not turned off DI11 because in a real canning application, you'd want to do this a bunch of times. So we're just going to leave it in positioning mode, and all the PLC has to do is trip DI12 again to do another cycle. Let's do that. You can see it's off doing its thing. The only way we can exit this is to turn DI11 off before it completes the positioning cycle. I'm going to do that right now. And that way it'll just sit and do nothing once that's over. We could reference it again, or we could go back into positioning mode. Eventually, as you can guess, we're going to extend the functionality of this program a little further. And as you can see, it seems to work just fine. So that's it. That's our first version of the canning and palletizing program. Okay, we're now going to learn our second positioning function. This one is almost identical to the first. In fact, there's almost no difference at all. This is the absolute positioning function. It's called GoABS, and it's got exactly the same parameters. The type is weight and no weight. Absolutely nothing different there. Again, if you use GoWait, it will not move to the next line until positioning is over. If you use no weight, it will continue immediately, and you'll have to figure out when it's finished. Positioning, again, is a constant or variable containing the distance in increments. The only difference is that position is treated as an absolute location relative to the machine zero location. It's not just an offset from where you're currently sitting. That is the only difference with GoABS. Now, it's probably time to point out a few system variables that you should be aware of that might be helpful to you in writing positioning programs. Let's look at our friend's status word in H473. It's got a lot of useful bits. For example, bit 3 tells you if the output transistors have been turned on the VFD. Bit 4 tells you if the magnetic field is rotating. Bit 5 tells you if the brake is released. Bit 6 tells you if the brake is applied. And here's a very important one, bit 19, it tells you that you have reached your destination. IPOS in position. If this bit is 1, it means you have successfully arrived. If it's 0, it means you're not there. Maybe you're in transit, maybe you're just not there and nothing's happening, but 1 tells you, yes, indeed, you have arrived where you want to go. H492, which is called target POS, contains the destination position of the current operation. If you execute a positioning function call, you will see the value that you give it appear in target POS, and we're going to find some uses for target POS down the road. ACT-POS ABS, which is an H509, this will give you the position based on an encoder that's connected to the X62 connector. That's only found on certain encoder cards. So if you've got an external encoder connected up there, you can read its position with this system variable. If you have an encoder connected to the X14 connector on an encoder card, its position is in ACT-POS Ext. And of course, there's our old friend ACT-POS motor in H511 that tells you the position based on the X15 connected encoder. So you can read several different encoders using different system variables. Of course, your application would have to have all those encoders. Just be aware of these. We're not going to mess with any of them except for the motor encoder in this class, but that's how you read other external encoders. All right, time for another hands-on task. This one will be a new program, but I, again, would simply copy program 9 because most of the code is the same. Call it program 10. What I want you to do is really simple. Just modify your previous program to use absolute positioning instead of relative. So you're just going to have to make a few quick tweaks, and it should work just fine. So go and do it. All right, let's see how you did. We'll take a look at my code and you can compare it to yours, and I imagine you probably did something relatively similar. All right, well, this is the absolute version of our positioning program. Since almost all the code is identical, I made a copy of program 9, renamed it to program 10, and you can see I brought this into my project now as program 10. This is going to take me just a minute to show you what's different. It's practically the same program, except that it's using absolute positioning. Here's the first area of difference. I had to change my positions. Notice now I am actually using the positions that I provided when I gave you that diagram of our palletizing line. That's because home is 0 That's what we treat as the machine zero position, and everything is relative to that. So now we can actually use those real positions that I gave you. So that is one difference. The times didn't change, of course, and none of the other constants changed. The code actually barely changed. The only thing that really changed is this section of the code here. Notice I'm using Go ABS instead of Go Rel, but I'm still using the weight version. I'm still passing it the same constants. So nothing else is really different. This is just a very minor tweak. It took me just a few minutes to make this change, and probably in your case it did too. Let's compile our code just to make sure it compiles fine, and we will run it. And I will give it a quick test and let you know what happened. I'm not going to show you this happening because if it works, it's going to do exactly what you just looked at a few minutes ago. The program worked exactly as the previous one did, so that is the end of our second program. So hopefully you found this as easy as I did. And now you're saying, wait a minute, I've just written two programs and now I've got to write another one? Yep, afraid so, but you're on a roll and this won't take too long. You're going to write a new program, program 11, but this will be based on program 10, so make a copy of program 10 because you can reuse most of the code. We're going to do just one change. We're going to switch to using real-world units. Notice I've given my positions now, instead of in increments, in millimeters. So you're going to change your program to use millimeters instead of increments. The times have not changed and the operation of the program has not changed. Almost everything is the same, but of course you're going to have to write some math code to translate real-world units into increments. Here are some of the guidelines. First of all, the program's behavior is identical to the previous version, but you need to use real units, and I suggest you go back and look at program number 3 because you can reuse some of that code to do the math part of this program. Of course, again, you should use constants for all your key parameters, and I've given you the mechanical parameters as well, like the roller diameter, the gear ratio, the encoder. I've also given you the positions and the times there as well. All these should be set up as constants, and your program, of course, should do the calculations, and it should create a variable called IPOScale that has the position scaling factor computed from the constants. And then positioning commands, and I suggest use absolute positioning, should use positions computed from the constants and the scaling factor, not hard-coded numbers. And of course, the reason we're doing that is because in a real-life situation, you would want to just change a few constants in your program if you change the application, recompile it, and have it automatically handle that. You shouldn't expect someone to go through and recompute a bunch of hard-coded values. So that's what I'd like you to do. And again, go ahead and pause the video and go do it. Okay, well that was our last program, so I'm sure you're tired, but let's see how you did. We'll compare your program to mine, and hopefully if you had any trouble with the math, this will explain it. All right, well this is our final program. It is probably the most challenging one because it's using real units and therefore it has to do some math. But it's still pretty much at heart the same code as the previous program. So I simply made a copy of program 10, renamed it to program 11, as you can see. And I've also brought up my old program 3 to borrow a few lines of code from it. So let's go through and talk about the changes between program 10 and 11. I'm going to put a special emphasis on the math, since that is the most challenging part. First of all, notice I have changed my position constants. I'm now using actual real unit positions in millimeters. So I did change that. And of course, I updated my comments to reflect that these are millimeters. My filling time, weighing time, palletizing time, those have not changed. But now I have a few constants for my mechanical parameters. I have my roller diameter, which is 50 millimeters. I have my constant for pi. I'm using 314, which is pi times 100. I'm using my encoder resolution of 4096 increments per revolution. And finally, my gearbox ratio, which is 4.25, I'm expressing that as 425, which is the ratio times 100. Notice I have commented this carefully. You should always comment math that does this kind of pseudo-fraction work. Otherwise, this could be really mystifying to someone who comes upon it for the first time. That's all the constants I need. Now I do need a few variables, so let's take a look at these. I'm letting IPOS pick where they go in memory. First of all, I have my distance, circumference, and encoder scale variable. This came from my program 3 code. I just copied that in here. I also have POS scale and also a variable called position. POS scale is ultimately what I'm going to head to. That's going to scale the real units into increments, and then position will contain the number of increments. We'll pass that to the goABS function. So this took a number of variables to accomplish this, but nothing too hefty. Moving on. I have my mechanical calculations in the initialization section because they only have to be computed once when the program starts. So I compute the circumference by multiplying pi times diameter. Then I compute the encoder scale by taking gear ratio times the encoder resolution. I then compute POS scale by taking encoder scale. I have to add 2 more decimal places, so I multiply it by 100, and then I divide it by circumference. That gives us our position scaling factor. And that is all the math we need. This is just straight from program 3. There's nothing different here. Moving along, nothing changed in the referencing code, but definitely a few minor changes in the positioning code. Notice before I go to my position, I first calculate position. I take the constant, in this case fill. I multiply it by POS scale and then divide by 100. That's to take out those pseudo decimal places. And then I go to position using goABS. So I calculate the position using the constant, the position scale. Then I actually pass that to goABS. I do that for each of these. Here's the next one right here. That's for the way station position. And then I have the palletizing one. And then lastly, I go to home. Now you may be thinking, well, wait a minute, home is 0, so why don't you just go to 0 and don't bother calculating it? Well, the reason I calculate it is because I want to give a future programmer the option to put home at someplace other than machine 0. There may be a reason to do that if the machine is modified. So I'm going to calculate that even though in this particular case it computes to 0. That's just a little bit of thoughtfulness for the future programmer who may have to modify this code. That is it. Everything else is exactly the same. So yes, it took a little extra work, but it wasn't anything too terrible, and naturally I did the heavy lifting for the math way back in program 3, and I'm glad I did because it's kind of late in the day and I don't really want to think so hard about math today. Okay, I'm going to compile my program just to make sure everything's happy here, and it is. I'm going to run it, and I'm going to do something extra. Whenever you get involved with a lot of these math calculations and you really want to be sure things are working right, it's a smart idea to call up a variable watch window and see what's going on to make sure that everything is computing correctly. Now, what I did before I came into the program is I computed everything by hand just on my pocket calculator to figure out what the numbers should be. Now, I've run the program here and I've located the variables. Remember, IPOS is picking them, so it put them starting at H420. And you can see it computed circumference, the encoder scale, and POS scale. And I've confirmed by just doing this by hand that these numbers are right. So my code does work here. What will be really fun to do, I have computed what the actual increments are for each position by multiplying POS scale times those millimeter positions. We should see position change as the code runs and as it positions. And so we can confirm it's going to the right places. When you're doing something like this, it's often smart to do that just to be sure you've got your math right and it's not going to some nutty position. Enough talk, let's go ahead and run it. You can watch the positions change. I am going to let you see this on the camera because we are using real distances, so the amount that it travels will be a little bit different. Since this is an absolute positioning application, I do need to reference my drive first. So I'm going to turn DI10 on and off to start referencing. You can see it's referencing. I've come onto the cam, come off the cam, and I've stopped. All right, I am now zeroed. I'm going to go ahead and start positioning by turning DI11 on, and I'm going to trigger positioning by pulsing DI12 on and off. And you should see it go through the different positions. And do watch the variable window as well. Watch the variable position, which is the last one, and you can see the different numbers come up as it gets ready to go to those positions. Here we go, triggering DI12. All right, there's the first one. There's the second one. There's the third. And now it goes back to 0. So there we go. Real-world units being translated to increments. And that is it. And that is it. That's the end of session number 10. You now understand how to position. Wasn't really that bad. Hopefully as well you're getting comfortable with translating between real-world units and increments. In our next session, we're going to move on to some very advanced topics. So maybe you want to get a good night's sleep before you tackle it, or at least buy a very large coffee somewhere and get yourself caffeinated, because we're definitely tackling some tough stuff next time. See you then.